This is one very easy problem to solve. We have equation for the position of an object in time, and all we need to do is to find first and second derivatives to determine velocity and acceleration. As the equation is polynomial, it becomes even easier. So, why to bother with this example in the first place? Because it will become more interesting and more complicated when we try to do something that is not a real goal of this problem. But in my opinion, this physics and not just pure calculus is more important. So, at some point, I will ask you to visualize the motion described by the given function. Even when we solve everything that is asked from us, it will be hard. But you will see it is very easy if you know to read the graph of the functions. Therefore, here we will learn to interpret the shapes of the function. To be precise, we will learn how shapes of function are connected to velocity and acceleration. So let's start. Here is given problem. The position of an object moving in a straight line is given by x equal to 3t minus 4t squared plus t over 3, where x is in meters and t is in seconds. A. What is the position of the object at t equals 0, 1, 2, 3, and 4 seconds? B. What is object displacement between t equals 0 and t equals 2 seconds? Between t equals 0 and t equals 4 seconds. C. What is average velocity for the time interval from t equals 2 seconds to t equals 4 seconds? For t equals 0 to t equals 3 seconds. Of course, it's very easy. Let's see the solutions. A. First, we need to say that the position of an object is always given by a position vector. So what is the meaning of this function? With this function, we actually calculate the magnitude of the position vector. And as you can see, all results in case A are vectors. In case A, we need to find positions of the object in 5 different moments. So, it's very easy. Just replace t in this equation with 0, 1, 2, 3, and 4. At the beginning of the motion, replace t with 0. The object is at the origin. At the first, second, replace t with 1. The object is again at the origin. So displacement is 0, but can we conclude that there is no motion in that period of time? Of course not, but let's proceed. When t is equal 2, we will have 3 times 2, that is equal 6, and then minus 4 times square of 2 gives 6, minus 16, that is minus 10, and at the end, minus 10 plus 2 over 3, that is minus 10 plus 8, which gives minus 2. So, the position of the object in the second is 2 meters in a negative direction. In the third second, the object will be at the origin again. And in the fourth second, the object will be 12 meters away in a positive direction. So, everything goes so smooth. But do we know the way the object was moving between these moments? Right now we don't. we do not have enough information to do so. Okay, let's go to the B case. We need to find two displacements, and displacement is a final position minus initial position. So all we need is here. Displacement between position 2 and 0, denoted with x2, 0, is equal to position 2 minus position 0, and it is equal to 2 meters in negative direction. Similarly, displacement between position 4 and position 0 is equal to 12 meters in positive direction. When it comes to case C, the average velocity, as it is known, is equal to displacement over elapsed time. So, in case of average velocity between position 4 and position 2, it is equal to the displacement between position 4 and position 2, which is 14 meters in a positive direction over elapsed time, which is 2 seconds. So the average velocity is 7 meters per second in a positive direction. And of course, average velocity between third and 0 time position is 0, because displacement between those two positions is 0. So we have done everything was asked from us in this problem. But I'm asking again, do we know the way the object was moving between 0 time position and position 4? Using only what we just calculated is not enough for giving precise conclusions about the way of the moving of the object. That's why we need something else and something more. As I have already announced, we will analyze the given function. So if we plot given function in xt plane, it will looks like this. We will analyze this function part by part. You can see 1, 2, 3, 4, 5, and 6 critical moments on t-axis. In what follows, we will see the meaning of each critical points. So let's look at the first part. We will analyze the motion of the particle between first and second critical point. Actually, from the beginning of the motion, precisely from the beginning of the observation of the motion to the point somewhere near 0.5 seconds. Can we conclude something from this part of the graph? We can see that as time goes, the particle moves away from the 0 points. Okay, but can we see what's going on with velocity and acceleration? Well, yes and no. Yes, if you have some previous experience. Someone experienced will tell you, yeah, the shape of the function in that interval is convex and the value of the function is bigger and bigger, so we are talking about a particle that is slowing down. But someone with no experience in this matter will say, what? What are you talking about? What is convex and what is bigger function and blah 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 blah. So let's talk about physics now. Let's look closer and take two equal intervals of time and then compare distances. It is obvious that the first distance is greater than the second one, and because particle travels those distances over the same interval, it means that the first speed of the particle is greater than the second one. So it means that the particle is slowing down, and we are talking about deceleration. Now let's go further and find first derivatives. Of course, you already know it is speed that we are talking about. You can see two graphs now. A is for distance and B is for first derivative or speed. Generally, we can discuss is it speed or something else, but here we can say it is a speed. Looking at the same interval between point 1 and point 2, at the B graph, we can confirm our previous statement that the particle is slowing. But also, we see something else. Look where the line at graph B are beginning. It starts from the point 0,3. What's that mean? It means that particle has initial speed of 3 meters per second. You can see it also if you put here t is equal to 0. Okay, now pay attention to this point here. At this moment, it is obviously that our function is at the local maximum. Or we can say that in observed interval, particle is located at the farthest point. Furthermore, if you look at the graph B, you can notice that in that moment, line is crossing the t-axis, so it means that speed is equal to 0. But remember calculus, if the first derivative of some function is equal to 0 in some point, then in that point function can have a maximum or minimum value. As you can see, first derivative or speed is equal to 0 at the two moments. So line crosses the t-axis at two places, at two moments. First is around 0.5 and the second is around 2 point something. Those numbers you can get by solving this to be equal to 0. So its first derivative or speed equal to 0. It's quadratic equation. I think now we have enough information to describe motion between point 1 and point 2. So we can say this. Particle starts with initial speed of 3 meters per second, then slowing down and stops around 0.5 seconds. Do not forget, this is straight line motion. So the motion looks something like this. Okay, we have graph for distance, graph for velocity, but what about graph for acceleration? We already mentioned that particle change its speed, so it's obvious that we have some kind of acceleration. Only thing we need to do is to find first derivative of speed to get function that describe acceleration. And that is this function shown in graph C. Now we have whole picture regarding the motion of our particle. We see that acceleration is not constant. It changes over time. Now let's observe the motion between around 0.5 and 2 point something. Why that interval? It seems that we skip 2 points. It's because the motion of the particle is such that particle is moving in a negative direction in this interval. So in this interval, particle starts from rest and stops at the moment 2 point something. So how can you explain such kind of motion? What can happen in between two zero speeds if you are moving? The only thing that can happen in such a case is that you start from a rest, then speed up, reach the maximum speed, and then slowing down until you stop again. Somewhere at the graph A, between 2 points with 0 speed, is one point in which looks like there is nothing special happening. It is at 1 point something seconds. But if you look at the graph B, you can see that in that point speed has some kind of extreme value. And if you look at the graph C, you can see that in that point acceleration is 0. From mathematical point of view, if the second derivatives of some function is equal to 0 at some point, then the function change its shape in that point. There are two possibilities. First, from convex it can become concave, and second, from concave it can become convex. In differential calculus, this point is called inflection point. So what happens in our case? It is obvious that inflection point is at the 1 point something seconds, and the curve goes from convex to concave. You can use the sign of the second derivative for that. If the second derivative is negative, then the curve of the function is convex. And if the second derivative is positive, then the curve of the function is concave. But let's talk about physics a little bit. Observe the motion from the second critical point near 0.5 seconds to inflection point. It is motion in a negative direction. Then you can see that particle is slowing down. Oops. Is it? Here numbers are smaller and smaller, but we are talking about speed. For example, number -3 is smaller than number -2. But speed -3 is actually speed of 3 meters per second in negative direction, and speed -2 is speed of 2 meters per second in negative direction. That is the case here. So here particle is speeding up in negative direction. And here you can see that acceleration is smaller and smaller until it reaches 0. Here again, numbers are bigger and bigger, but acceleration is smaller and smaller. Okay, summary. Particle is moving in a negative direction, speeding up until it reaches maximum speed. Acceleration is smaller and smaller until it reaches 0. So the motion of the particle in observed interval looks like this. I'm sure we can go faster now. Let's see what's happened from inflection point to point at the 2 point something second. But let's talk in physics language. Particle is moving in a negative direction until 2 point something second, when it is farther away from 0 point, but in negative direction. Particle is slowing down until it reaches 0 velocity, and acceleration is bigger and bigger. It's not mistake. Listen again. Slowing down and acceleration is bigger and bigger. How can we have acceleration and particle to slowing down? Simple, because acceleration point out in a positive direction and particle is moving in negative direction. That's why the acceleration actually is taking away some meters per second every second of the speed. So the motion of the particle in the observed interval is looking like this. Let's now look at the motion between 2-point-something seconds and third second. Again, let's talk in physics language. Particle is moving in a positive direction, is speeding up, and acceleration is bigger and bigger. The same is for motion between third and fourth second. Particle is moving in a positive direction, is speeding up, and acceleration is bigger and bigger. So the motion between 2-point-something and 4 seconds looks like this. Finally, we can show the whole motion of the particle from 0 to 4th second. Therefore, we have this. The particle has initial velocity and moves in a positive direction. Slows down until it stops. Then goes in a negative direction, speeds up, goes through 0 point, reach the maximum velocity in this interval, then slowing down until it stops. Then go again in a positive direction, speed up, goes through 0 point again, and speed up again. Also, have a look again several times.